What's up, guys? Welcome back to another Grind 75 video walkthrough. Today we're going to be going over Leetcode number 127, word ladder. So we're given we're tasked with trying to find a transformation sequence from the word begin word to the word end word using a dictionary word list, which is a sequence of words, begin word to, um, just like a sequence of words, basically such that each adjacent pair of words differs by a single letter, and every connecting word between these two words is in the word list. Note that begin word does not need to be in the word list, and SK is the end word. So given these two words and a dictionary word list, return the number of words in the shortest transformation sequence from begin word to end word, or 0 if no such sequence exists. Some examples are as follows. Begin word is hit and end word is cog. And the word list is hot, dot, dog, lot, log, cog. So um, the output we should return is 5 because one such shortest transformation sequence goes from hit to hot to dot to dog to cog, which is 5 words long. Right, so notice how in between each of these words, it only differs by one letter. So between hit and hot, the I and O differ, and between hot and dot, the H and D differ, and so on, right? In our second example, though, cog isn't in the word list, so there's no valid transformation sequence, so we just return 0. So that's like a preemptive check that we have to do before we can even start doing any sort of algorithmic processing. So a high-level approach for this is to use the BFS algorithm, because this is basically a graph problem where each node is a word, and then there's edges between words that differ by only one character, right? So what we can do is use BFS to find the shortest path from one word to another using only edges. So uh, before we can use BFS, what we first have to do is initialize a pattern to word mapping for each word in word list. And I'll go over what this means in the walkthrough. But yeah, we'll also have to maintain a visit set and a queue, which initially just have the begin word in them to start out with. We also have to keep track of the path length with another variable, and we'll initialize this to 1. And then we can start the execution of this algorithm, right? So we have a while loop that checks while the queue is not empty. And then while that's true, basically what we do is we process all the words that are in the queue at the start of the execution of the while loop. And for each word, we compute all the missing letter patterns and add non-visited words from those patterns into the queue. And if a word taken from the queue is the end word, what we do is we just return the path length. Else, we increment the path length by 1 after each round of processing. So going over this example in more detail, we have this begin word, hit, and end word, cog, and we have this word list of 6 words. And cog is in here, so we don't have to exit out immediately. Uh, we can try to find the path. So step 1, we initialize the pattern mapping. So basically, this is what I was talking about in the first step. So let's say you have a word like hot, then all the patterns where um, where a word that belongs to each pattern is different from hot by only one letter, it can be computed as follows, right? So you just have hot, and then HT, and then HO. So these are all the patterns, and if a word fits into this particular pattern, then it's only one different letter from hot, which means it's basically it has an edge between it and hot, right? So what we do is for each word in this word list, we go through every word and then we compute all the possible patterns. And then if a word belongs to any such pattern, we basically add it to its respective list. And at the end of processing, we have a list of all the words that belong to each pattern. And we'll call this dictionary NEI, which stands for neighbors. And now step 2 is BFS. So what we're doing here is we're processing from the queue and basically adding to the queue all the words that are one letter different from the word we're processing until we find the word that is the end word, which is cog in this case. So right now we have visited as hit, queue as hit because this hit is the begin word. Um, res is the result we want to return, and it's initialized to 1 because it's just the start of the execution. And the length is also equal to 1 because the queue is length 1 when we're starting. And yeah, let's start processing. So we'll get rid of this. So our word is hit. All the patterns are H or star IT, H star T, and then HI star. So star IT and HI star are not a pattern, but H star T is, and all the words in H star T are hot. So what we can do is let's put hot in visited and then add it to our queue. And oh yeah, so we'll just do I equals 0, and now I is 1. So because it's the same as the length, we have to start over again. So length is still 1. And yeah, we have to increment result by 1 because we finished the first layer. And we start again. So take hot from this queue. All the patterns are star OT, H star T, and then HO star. So we add this, this, this. So we add all of those to the queue and put them in visited as well. So we don't add hot because it's already in visited, but we do add dot and lot. And then let's just add these to the queue. And we will increment I by 1, see that it's the same as length, so go back. Now the length of the queue is 2, and then we increment res by 1, so it's 3, and resume processing. So we'll take in dot now. All the patterns are OT, D star T, and DO star. So star OT we've already processed, and we can see that every word in star OT is already visited, so nothing to add from that. D star T, the only word in there is dot, but as we can see, we already have dot in the visited set, so we don't have to add that as well. And then lastly, DO star, we do see that there's one new word, which is dog, so we can um, add dog to both visited and the queue. And we resume processing, so now I is 1. The word that we're going to process now is lot. And then the patterns for this are star OT, L star T, and then LO star. So star OT, we visited that already. L star T, that just has lot, and we've already visited that. Then LO star, we have lot and log. And log is something we haven't visited. So what we do is we add log to visited, and then add log to queue. And increment I by 1, and now we see that it's the same as length, so we can reset. Yeah, so the length of the queue is 2 right now, so we'll initialize length to be 2. Increment res by 1, and resume processing. So now our word is dog. Dog patterns are star OG, D star G, and then DO star. Star OG, we have dog, log, and cog. Cog is a new word, so let's add that to the queue and visited. D star G, that's just dog, and then DO star, that's also dot and dog. Both of those are already visited. So, yep, dog is done. We go to log now. So log, the patterns are LO star, L star G, and then star OG. So star OG, we don't even have to check. We've been knowing that that's already been visited. L star G, that's log that's been visited, and then LO star is lot and log, both of which have been visited. So we add nothing to the queue in this round of execution. Increment I by 1. See that it's the same as length, so this round has been finished. What's remaining in the queue is only cog, so our new length is 1. Increment res by 5. And yeah, recommence the processing. So now our word is cog. And yep, this is the end word. So what we return is the res. So our solution is 5. And this was simply another BFS iterative algorithm where the general structure of this was a for loop listed within a while loop and then um, incrementing res, right? Whenever there's a BFS problem, this is the general structure that should be used. Um, this was also in the routing orders problem, so if you revisited that problem, you can see a lot of similarities with that and this. And yep, that's basically it.